In this section, we will not enumerate a whole list of optimization techniques, but we will present some of the generics, touch upon some of the tools, and we'll present a case study which shows that once you have a target in front of you, how you can go about systematically figuring out how to optimize your code. Now, the essential part of optimization is not to just apply techniques or use pattern matching just for the sake of optimization, but essentially to first understand what is your state of performance and where do you need to go. So essentially you need to profile your current state of performance in terms of your code's elapsed time, CPU time, IOs, whether you're looking at tools that will give you system metrics or tools that will give you elapsed time metrics. Once you know where you stand and you know where you have to go, then you start going about optimizing by finding out where are your bottlenecks and how do you go about budgeting the time available to you, because there is no end to where you can optimize given that it is humans who are writing code. You need to then look at how do you prioritize your bottlenecks, how do you look at the ones that occur most frequently. Most likely the bottlenecks are the ones that are there in loops of code because they are going to be called very frequently. So look at which objects are called often, look at what needs to be optimized with respect to frequency and time, and then repeatedly go through the cycle of profiling and optimization. Now, in the past it was common to put a number of timestamps in the code, but in the last decade or so there have been a huge number of profilers available, which makes it very simple for developers to find out bottlenecks. Now, from the web tier level at the browser itself, you have nice tools such as HTTP Watch or Fiddler that can be enabled in record option, and they give you a complete trace of all the lower level calls made for the URLs that you clicked. So you get to know individual HTTP requests, you get to know sizes of requests, you get to know number of round trips, and you can accordingly figure out, especially over a wide area network, where is the time being spent. For Java applications, there are nice tools available as well. Some of the very popular ones are Wiley Introscope and HP J2E Deep Diagnostics. That can give you a complete profile of individual methods called. There is nothing that you need to do in your code. They will simply take your jar files and put in the appropriate instrumentation. And you also get JProfiler and Gensor, which can be used if you are worried about costs, although they may not be as versatile as Introscope of Deep Diagnostics. At the database level, the most common way of detecting the path in which your query is taking is to run an explain plan, and you have individual tools such as TKProf or Oracle AWR reports for Oracle. You have DB2 PM for DB2 and SQL Profile for Microsoft SQL Server. For Intel platforms, there is vTune, which is a very useful tool, and IBM also has Quantify and Purify for C++ applications. vTune can be used for C++ and Java applications. Mainframes, you can have Strobe and OmegaMon, and if you need to know an end-to-end perspective of what's going on, especially by tapping the network and getting to know what's the time spent between the browser and the web tier, the web and the app tier, the app and the database tier, including individual calls made and patterns that are being communicated, then tools like Wireshark, iWatch or Pastemon are very useful. You can also use OS level tools such as dtrace for Solaris or Caliper for HP Unix and RMF for mainframes, because they will give you a very nice trace of what's happening in your system at an individual thread level, and you can correlate it with aspects of system resource consumption, including IOs and memory and CPU and so on and so forth. Now the tools give you a whole lot of data. You need to be very selective in what you're going to do with the data, because the application that we deal with today are not just 10 lines of code, they run into millions of lines of code. And even if you did not have tools, you could have always put timestamps to get the data. But the problem comes in the next stage, that you cannot go about finding out bottlenecks and optimizing each and every bottleneck. You need to make some assumptions that given a large amount of code, usually this Pareto rule applies that more than 80% bottlenecks lie in less than 20% of the code. So you can narrow down to the individual regions of code that are having the biggest number of bottlenecks and check out the ones that are consuming the most amount of time or are being called most frequently. We mentioned about demand in the architecture and design stage. So tune the ones that have highest demand and then go about iteratively tuning and profiling. Now when it comes to optimization, profilers help you figure out where are your problems. To fix the problems, you can try out a number of techniques, and we'll not get through these in the slide deck here, but instead I'll give you these pointers. For databases such as Oracle, there are some very good links like the first two. For Java optimization, precise-java.com is an excellent site. For Microsoft.NET, you can go to msdn.microsoft.com, the link provided there. And likewise, the next one is for C++ optimization. And then the next two are for website optimizations, where you can optimize your web page design and implementation. So there are a whole range of techniques available, and depending on where you have encountered the bottleneck, you can selectively choose which are the ones to apply. Now let's move on to a few optimization techniques which are generic in nature. The idea is, in the least amount of time, how do you detect the patterns that need to be fixed? Well, the first thing to keep in mind is that wherever relevant, use compiler optimization flags. For example, if you're in C or C++, you can use a -03 in most systems, as Unix systems in particular, and you can very comfortably get in the range of 5 to 20 to 30% speed up in your code by doing nothing but using optimization flags. The other aspect is, which compilers normally take care of it, but you will be in a better position to decide, especially when there are functions and other aspects that compilers may be confused about, is to take loop invariant computations and move them out of the loop. It could be that for the sake of readability or out of sheer redundancy, some invariant computations crept into the loop. You should also keep in mind that a lot of our applications deal with string processing, and CPUs are much better at number crunching. So wherever relevant, replace strings with numeric codes, so that if you look at operators such as comparison, when to compare two strings, it's going to actually compare byte by byte, and that's going to be an awful lot of time. Whereas the same thing, if you have numeric codes, it can just be done in probably one clock cycle in terms of the comparison. Very often performance goes for a toss because of redundant objects that lie in the code. Not only do they take up a lot of memory, they can also waste a lot of cycles. When it comes to aspects dealing with database transactions, you should avoid full table scans and look at where all you can have the right indexing structures, and for that purpose choose the right data structure and algorithms. There's also a whole lot of memory available in computers today, so try to make sure that a lot of data is available in the memory, whether you build your own custom data structures or you use some third-party tools. But not only do these help speed up access, it also avoids costly communication from applications to databases. The point number 8 is quite important as well, that there is a tendency in object-oriented systems to do a lot of joins on the application server. So if you take the sample code on the left, See, if you have two objects and you wish to join them, so you say for every row in object 1, fetch the row and then join it with a corresponding row in object 2. And these nested loops joins is going to be an extremely costly aspect of access when it's done in the application server, because you could have millions of rows in their persistent objects. On the contrary, you could just make one call to the database instead of millions of calls and do the join in the database itself, preferably by calling through a stored procedure call or a simple SQL call that has the selects embedded in it. So essentially you can save a lot of these communication overheads by doing the joins in the appropriate places. Let's take a case study to make it more interesting. Right, this deals with the risk management computation where we are just showing you one subset of the entire work, where the target was 10,000 trades per second. The initial baseline that was created in C code was 190 trades per second on a single thread, and it was thought that, well, why don't we go for a 64 CPU machine so that we can scale from 190 trades per second to 10,000 trades per second. The client had a budget crunch and was ready to give only 8 CPUs. Now you have to keep in mind is, if we had jumped from one thread to 64 CPUs, it's not necessary that we would have got a 64-fold speed up. On the contrary, we could have had a very hard time optimizing and trying to get the threads to scale. But given the constraint that we had a much smaller number of CPUs, we had to do a lot of single thread optimization before we decided to parallelize. And therefore keep that as a significant learning, that always thrash out single threaded performance before moving on to parallel programming, because it is very difficult to debug parallel programs. So let's take the single thread and let's see how the optimizations were done. Well, here is the code in front of you, a sample code. We'll not go through it line by line, just point you to two of these boxes. The blue box on top refers to the declarations. Essentially these are two-dimensional arrays except for the Prophet, which is a one-dimensional array. Let's not worry too much also about what they stand for and what they do. They are self-explanatory, but in interest of time I'll not get into as many details. There's a yellow box which is an inner loop that does the major part of the computation. That is, for every trade, t equal to get next trade, it takes the stock of that trade and then goes through the Prophet computations in the manner shown in the inner loop. Now the baselining that was done was to take a trade file of 1 million trades that was synthetically generated, have 100,000 traders, and have a skew that 60% of trades occur on 10% of stocks. So benchmark was done, or a baseline was done using a single thread on the Xeon system with CentOS 5.3, and the baseline performance with the GCC compiler, as we said, was 190 trades per second. Now by doing nothing other than applying the O3 optimization flag and recompiling the code, we're able to get a nice 70% gain, so that the trades could jump to 323 per second. So this was still far off from a target of 10,000 per second, but shows you the benefits of using optimization in the compilation flags. Now one of the important aspects of optimization is to look at how well are you caching objects. So if you look at these various data structures that we had defined, it's nothing wrong in what we have chosen, but if you look at the way in which the code is executed, the inner loop is for a given trade you run through all the traders. That means for a given stock you run through all the traders and do the computations. But if you look at the way the two-dimensional structures are defined, they are, the first dimension is a trader and second dimension is the stock. So essentially what we are doing is we are actually taking a stock and traversing the traders, and in that sense we are actually very poor in caching, because if we take for example a stock SI, we'll first access data for trader R1, then we'll access data for trader R2, and that's not the way in which data is actually stored. So we are actually skipping a lot of elements before we get on to the next trader, and this can be very poor in terms of caching. So essentially what should we do? Well, if we wish to improve the caching and we are going to access the data for a given stock and run through all the traders, it's much better if the traders are stored in columns and the stocks are stored as the rows. So essentially what we do is we actually store it as a transpose of the previous matrix. So you'll notice in the declarations we have actually transposed the order of stocks and traders, and in the inner loop as well we have just transposed the dimensions of stocks and traders. So now if we look at this figure for a given trade T and a given stock SI, we are actually accessing the data across all the traders in the manner in which the system will store them, in the manner in which they will be stored in the memory and in the cache, and every cache line fetched is actually going to contain all the data that we need for the inner loop to be accessed very fast. Now just a simple change, which is not a major code change, yielded tremendous benefits, and as you can see from 323 trades per second we jumped to 4750 trades per second, an overall gain of 25 times compared to our initial baseline. At that stage we had also got an Intel compiler, which was a commercial compiler unlike the free GCC one, and by using a -fast option we were able to get an additional benefit of going from 4750 to 6850 trades per second. So that was roughly close to almost 40% improvement, to give an overall gain of 36x. Now then we thought about it, that is there a way to do the caching even better? Well, if you look at the yellow box, we have these three two-dimensional arrays: net position, sum, transaction value, profit per stock, and in the inner loop they are actually accessed using the same dimensional elements. So for the same stock and for the same trader we are accessing all these three two-dimensional arrays in the same place, but by declaring them as separate arrays we are actually spreading out the locations, and this is also going to be detrimental for caching, because a cache is not going to pin these individual arrays separately. It will get an element of the first two-dimensional array, then it will get an element of the second two-dimensional array, and then the third two-dimensional array, and it would have been much better if these arrays were clustered or co-located. So the way to do that is to simply declare this as one object rather than three separate objects, and we can use that as a struct in C. So we create a trader record with these three individual attributes of positions, transaction values, and profit per stock, created as one two-dimensional array, and this clustering technique straight away boosted us to a throughput of 12,000 trades per second with an overall gain of 63x compared to the baseline. So essentially we started out with the objective of having 10,000 trades per second on 8 CPUs. We actually achieved it on one CPU. And just for the kick of it, we took this 12,000 trades per second. We decided we'll take the single thread and parallelize it right now using OpenMP with a very simple pragma directive, and we were able to get, without much effort, another 2.5x increase, so that we effectively landed up with 30,000 trades per second on 8 CPUs. So that was about an example with code optimization, and essentially showing you that if the target is clear and in front of you, you will find out ways and means of achieving the target. But quite often the target is never that transparent to an individual developer. Now if you have an end-to-end requirement, let's say for response time, how do you translate it to a lower level target for a given developer who's only concerned about his own servlets or her own SQLs that need to be optimized? So let's take an example. Let's say you're given a banking application with a workload of 3000 users with an end-to-end response time of 2 seconds and a think time of 28 seconds. And let's take a very simple case that for a given request or a given service call, there is a single servlet, and that servlet makes 5 database calls on the average. Now you need to know is what should be the service time target for a developer for the servlets, and what is the service time target for a developer for the database calls, so that you know in how many milliseconds this call needs to complete. Alternatively, in case you are not able to meet the targets, then what is the number of CPUs required to be planned per tier? This is actually not as difficult, it's quite simple, but we will not take it up in this course. We'll deal with it when we come to a performance modeling course, and we'll show you that how with very simple demand modeling techniques we are able to tell you what is the target per developer. Because as I said, once the target is known, it gives you a drive to be able to optimize towards the target. Otherwise, if no target is specified, it's always somebody else's problem when you're dealing with an end-to-end performance management.